Hi, welcome to Unsupervised Learning in Python. Unsupervised learning encompasses a variety of techniques in machine learning, from clustering to dimension reduction to matrix factorization. In this course, you'll learn the fundamentals of unsupervised learning and implement the essential algorithms using scikit-learn and scipy. You will learn how to cluster, transform, visualize, and extract insights from unlabeled datasets, and end the course by building a recommender system to recommend popular musical artists. This course consists of 4 chapters, which are clustering for dataset exploration, visualization with hierarchical clustering and TSNE, decorrelating your data and dimension reduction, and lastly, discovering interpretable features. In this video, you'll learn about a dimension reduction technique called non-negative matrix factorization, NMF, that expresses samples as combinations of interpretable parts. For example, it expresses documents as combinations of topics, and images in terms of commonly occurring visual patterns. You'll also learn to use NMF to build recommender systems that can find you similar articles to read, or musical artists that match your listening history. Let's begin with non-negative matrix factorization. NMF stands for non-negative matrix factorization. NMF, like PCA, is a dimension reduction technique. In contrast to PCA, however, NMF models are interpretable. This means NMF models are easier to understand yourself, and much easier for you to explain to others. NMF cannot be applied to every dataset, however, it is required that the sample features be non-negative, so greater than or equal to 0. NMF achieves its interpretability by decomposing samples as sums of their parts. For example, NMF decomposes documents as combinations of common themes, and images as combinations of common patterns. You'll learn about both these examples in detail later. For now, let's focus on getting started. NMF is available in scikit-learn, and follows the same fit/transform pattern as PCA. However, unlike PCA, the desired number of components must always be specified. NMF works both with NumPy arrays and sparse arrays in the CSR_matrix format. Let's see an application of NMF to a toy example of a word frequency array. In this toy dataset, there are only 4 words in the vocabulary, and these correspond to the 4 columns of the word frequency array. Each row represents a document, and the entries of the array measure the frequency of each word in the document using what's known as TF-IDF. TF is the frequency of the word in the document. So if 10% of the words in the document are datacamp, then the TF of datacamp for that document is 0.1. IDF is a weighting scheme that reduces the influence of frequent words like the. Let's now see how to use NMF in Python. Firstly, import NMF. Create a model, specifying the desired number of components. Let's specify 2. Fit the model to the samples, then use the fit model to perform the transformation. Just as PCA has principal components, NMF has components which it learns from the samples, and as with PCA, the dimension of the components is the same as the dimension of the samples. In our example, for instance, there are 2 components, and they live in 4-dimensional space, corresponding to the 4 words in the vocabulary. The entries of the NMF components are always non-negative. The NMF feature values are non-negative, as well. As we saw with PCA, our transformed data in this example will have 2 columns, corresponding to our 2 new features. The features and the components of an NMF model can be combined to approximately reconstruct the original data samples. So a sample can be reconstructed by multiplying the NMF components by the NMF feature values of the sample, and adding up. This calculation also can be expressed as what is known as a product of matrices. We won't be using that point of view, but that's where the matrix factorization, or MF, in NMF comes from. Finally, remember that NMF can only be applied to arrays of non-negative data, such as word frequency arrays. In the next video, you'll construct another example by encoding collections of images as non-negative arrays. There are many other great examples as well, such as arrays encoding audio spectrograms, and arrays representing the purchase histories on e-commerce sites. In this video, you'll learn that the components of NMF represent patterns that frequently occur in the samples. Let's consider a concrete example, where scientific articles are represented by their word frequencies. There are 20,000 articles, and 800 words, so the array has 800 columns. Let's fit an NMF model with 10 components to the articles. The 10 components are stored as the 10 rows of a 2-dimensional NumPy array. The rows, or components, live in an 800-dimensional space. There is 1 dimension for each of the words. Aligning the words of our vocabulary with the columns of the NMF components allows them to be interpreted. Choosing a component, such as this one, and looking at which words have the highest values, we see that they fit a theme. The words are species, plant, plants, genetic, evolution and life. The same happens if any other component is considered. So if NMF is applied to documents, then the components correspond to topics, and the NMF features reconstruct the documents from the topics. If NMF is applied to a collection of images, on the other hand, then the NMF components represent patterns that frequently occur in the images. In this example, for instance, NMF decomposes images from an LCD display into the individual cells of the display. To do this, you'll need to know how to represent a collection of images as a non-negative array. An image in which all the pixels are shades of gray ranging from black to white is called a grayscale image. Since there are only shades of gray, a grayscale image can be encoded by the brightness of every pixel, representing the brightness as a number between 0 and 1, where 0 is totally black and 1 is totally white. The image can be represented as a two-dimensional array of numbers. Here, for example, is a grayscale photo of the moon. These two-dimensional arrays of numbers can then be flattened by enumerating the entries. For instance, we could read off the values row by row, from left to right and top to bottom. The grayscale image is now represented by a flat array of non-negative numbers. A collection of grayscale images of the same size can thus be encoded as a two-dimensional array, in which each row represents an image as a flattened array, and each column represents a pixel. Viewing the images as samples, and the pixels as features, we see that the data is arranged similarly to the word frequency array. Indeed, the entries of this array are non-negative, so NMF can be used to learn the parts of the images. It's difficult to visualize an image by just looking at the flattened array. To recover the image, use the reshape method of the sample, specifying the dimensions of the original image as a tuple. This yields the two-dimensional array of pixel brightness. To display the corresponding image, import pyplot, and pass the two-dimensional array to the plt.show function. Let's move on to building recommender systems using NMF. Suppose that you are an engineer at a large online newspaper. You've been given the task of recommending articles that are similar to the article currently being read by a customer. Given an article, how can you find articles that have similar topics? In this video, you'll learn how to solve this problem, and others like it, by using NMF. Our strategy for solving this problem is to apply NMF to the word frequency array of the articles, and to use the resulting NMF features. You learned in the previous videos these NMF features describe the topic mixture of an article. So similar articles will have similar NMF features. But how can two articles be compared using their NMF features? Before answering this question, let's set the scene by doing the first step. You are given a word frequency array articles corresponding to the collection of newspaper articles in question. Import NMF, create the model, and use the fit_transform method to obtain the transformed articles. Now we've got NMF features for every article, given by the columns of the new array. Now we need to define how to compare articles using their NMF features. Similar documents have similar topics, but it isn't always the case that the NMF feature values are exactly the same. For instance, one version of a document might use very direct language, whereas other versions might interleave the same content with meaningless chatter. Meaningless chatter reduces the frequency of the topic words overall, which reduces the values of the NMF features representing the topics. However, on a scatter plot of the NMF features, all these versions lie on a single line passing through the origin. For this reason, when comparing two documents, it's a good idea to compare these lines. We'll compare them using what is known as the cosine similarity, which uses the angle between the two lines. Higher values indicate greater similarity. The technical definition of the cosine similarity is out the scope of this course, but we've already gained an intuition. Let's see now how to compute the cosine similarity. Firstly, import the normalize function, and apply it to the array of all NMF features. Now select the row corresponding to the current article, and pass it to the dot method of the array of all normalized features. This results in the cosine similarities. Thanks for watching and congratulations, you sure have come a long way. You've learned all about unsupervised learning, and applied the techniques to real-world datasets, and built your knowledge of Python along the way. In particular, you've become a whiz at using scikit-learn and scipy for unsupervised learning challenges. You have harnessed both clustering and dimension reduction techniques to tackle serious problems with real-world datasets, such as clustering Wikipedia documents by the words they contain, and recommending musical artists to consumers. You are now equipped to face a whole range of new challenges. Congratulations, once again. If you have any questions, please ask them in the comments section. Like and subscribe to stay updated about our upcoming videos about artificial intelligence. See you in the next video.